Hello? How are you? It's really a real privilege and honor to introduce our featured guest today, one of the people who has helped shape modern computing and AI, Jeff Dean. Jeff. Jeff joined Google in 1999, and over the next 29 years, or 27, helped build many of the foundation of modern computing and AI, from MapReduce to Bigtable to TensorFlow to Google Brain. His contribution has been recognized at the highest levels. He is an elected member of National Academy of Engineering. He is recipient of both the IEEE John von Neumann Medal and the ACM Prize in Computing. And now Jeff is beginning a new chapter, and today is his first day here at Stanford. That makes today very special and exciting. So I can't think of a better person to have this conversation with Jeff than Dong Song. Dong, please. Dong is one of the leading researchers at the intersection of AI, security, trustworthy computing. Her work at Berkeley has been enormous. She is a MacArthur Fellow and an elected member of the American Academy of Science and Arts, or Arts and Science. He is also a great startup professor. He had 4 startups that one of them reached 100 million revenue. What I have always admired Dawn is she doesn't just stop doing great research, but also really turn that into real impact. Just like Jeff, Dawn also is beginning a fascinating new chapter from Berkeley to Meta, one of the largest organizations on AI. So we have an interesting contrast today. Dawn is moving into a large platform, and Jeff is leaving a very large platform to start something new. Apparently, even among the 2 best people today on stage cannot agree what is the optimal size of a company doing AI. So I can relate a little bit myself. After 30 years working at Microsoft, I joined Zoom. So perhaps the real lesson is simple. It's not about the size of the ship. It's about whether there's a new exciting blue ocean worth exploring. And AI today is absolutely that new blue ocean. The last decade has been about making AI more capable. Now, the next chapter raises the bar for us to answer even more important question. What can we actually accomplish with all of this great intelligence? Can AI cure cancer? Can AI make our society better? Those are some of the questions I hope we can explore today. So please join me in welcoming our fireside chat, Jeff Dean and our moderator, Dong Song. Thank you.
Great. Thanks a lot for joining us, Jeff.
Yeah, thank you.
Really excited. I mean, the whole entire auditorium, everyone's really excited. So before we start, so first, just some personal notes. So Jeff and I, we have known each other for a very long time, more than a decade. I wanted to just briefly share actually one of my most memorable moments, interacting and talking together with Jeff. So this is a long time ago, almost a decade ago. So around iClear 2017, so iClear is one of the top machine learning conference. Back then it was much smaller. It was actually only like a few hundred people. Now it's like tens of thousands of people. So remember at iClear, so my group actually, our paper won the best paper awards that year at iClear for a paper on generalization for neural program synthesis. This is actually way before now LM-based code generation. So Jeff, thank you so much. So I don't know whether you remember, you actually came to me to congratulate me for the best paper award. And Jeff told me, at this iClear, there are 3 best paper awards, 1 from me, my group, and 2 from Google. So that was, thanks a lot, that was very memorable.
That was a very good paper you wrote. So.
No, thank you, thank you. And also I remember how excited you were at the time, then telling me about one of your recent work back then, which is actually, a mixture of experts. So, I mean, the paper is titled, of course, back then it's a longer title, it's Outrageously Large Neural Networks, the sparsely gated mixture of experts layer.
Yeah.
Yes, so when I was listening to you explain to me about the paper, I thought, wow, it's really fascinating. But however, back then, I didn't foresee, I don't know whether you even, could have foreseen how influential the work has become. Essentially, it has underpinned now almost all frontier AI models are all MOE architecture.
Yeah, I mean, I think the intuition behind the MOE work was really that you want to have really, really large models that have a lot of capacity to remember lots of things, but that you want to make them efficient by only calling on the parts of the model that are most useful. And you can have kind of modular architectures where you have lots of different kind of experts, and you learn which experts are good at which thing, and then when you're in the context of processing a particular request or a particular token, you can activate just the portion of the model that makes sense for that token, right? Like you have, in a real brain, you have lots of different pieces of your brain that are good at different things. There's one that's thinking about Shakespearean sonnets. There's another that's like active when there's a garbage truck backing up at you while you're driving. And those are not active at the same time. So it makes sense to save energy to be able to have very large capacity and then find the right pieces of the model to activate. So we were pretty excited about that. And that was one where we sort of knew it was going to be a big deal because we could see like 10x better sort of training compute to quality ratios than if you had dense models, which were kind of the main thing people were using at that time. So, one of these ideas where you see 10x improvements, you're like, okay, that's pretty significant. It's probably going to be an important idea. So.
Yes, yeah, it's amazing. I mean, even just listening to your explanation now, actually, it's quite similar even to the explanation back then when you, when you were explaining to me. So it's amazing, the timelessness of the idea. Yes, so Jeff, you have done so much work, amazing work, looking back in the past decades. Essentially, over the past several decades, you've helped shape nearly every major computing platform, and also many key advances behind modern AI, from MapReduce and Bigtable to TensorFlow, TPUs, and MOE, and Gemini. So yes, we have really a lot to talk about. So looking back, what has surprised you the most about the trajectory of AI over the past decades? And is there something you think the field is still underestimating today, or missing today?
Yeah, I mean, I think obviously there's been a lot of growing interest in AI starting. We were starting to do work on scaling up deep learning models in maybe 2011, 2012 was kind of when we really started that at Google. And, we were starting to see amazing results from training neural networks, say, that were 50 times bigger than had previously ever been trained. And you would get like amazing reductions in, image classification error rates, speech recognition improvements were kind of like equivalent to the previous 20 years of speech research in terms of lowering error rate by just scaling up a fairly simple, deep acoustic speech model. So we sort of saw that trend pretty early and knew this was going to be important for all kinds of different, things in, really hard computer science topics like computer vision or language processing or speech recognition. And I think one nice thing about kind of the deep learning paradigm is it's really unified a lot of these fields that were previously kind of had separate kind of particular techniques that the fields were working on. And by essentially learning from very raw forms of data, we've been able to have these, kind of paradigm shifting things where all of a sudden you squint at problems differently with this general learning lens that has been really helpful. And I think over the last, say 15 years, more and more people around the world in more and more kinds of disciplines have really just realized that this is an extremely powerful way to model data, to be able to make predictions, to be able to make important kinds of classifications in medicine and science and consumer products and chatbots and all the kinds of things you're now seeing. I guess the level of investment in the compute hardware and so on is quite large. So I think that's a sign that people are confident in the ability of this technology to change the world even more than it already has. So that's kind of interesting and exciting. So I guess that would be a summary of what's been happening.
Yes, yeah, thanks. And we'll talk about now, you'll be even further in the journey with your new startup. We'll talk about it in a few minutes. And so again, you've done so many really foundational, seminal work. We don't have time to go through them all. So maybe just a couple of them to share more of your the lessons and insights that you have learned. So let's take one example, TensorFlow. So TensorFlow really helped make modern deep learning accessible to millions of researchers and developers around the world. So when you designed TensorFlow, what principles mattered the most? And looking back, what would you design differently today? And what lessons from TensorFlow do you think should guide the next generation of AI frameworks for increasingly agentic AI systems?
Yeah, I mean, I think we had built a previous system within Google that was not open source called Disbelief that had a way of expressing various kinds of neural network computations and then could map those computations onto various kinds of hardware platforms, CPUs, GPUs, and it would distribute computation in a way that was kind of seamless to the user. So you could say, I want to train this model, I want to use 100 computers and 1,600 cores, or I want to use 500 GPUs or whatever. And then the framework underneath would take care of that. And so we wanted to bring that kind of, the ability for the ML researcher or developer to be a little bit abstracted from exactly how it's mapped onto the compute hardware, because that's a really nice, elegant abstraction. You can say, I just have this beautiful ML model in my head, and I don't care how you implement it, but please make it run really fast. So that was one of the things we wanted to bring to TensorFlow. And then we wanted to generalize the kind of computational abstractions we were providing to be just a combination of a computational graph of various kinds of ML-oriented operations like matrix multiplies and vector operations and so on. So I think we got that reasonably right, and we wanted to open source this so that people all over the world who have machine learning problems could start to take advantage of being able to have a common framework to express those ideas. It's much nicer when you have say a research paper that comes with a implementation of the ideas in the research paper rather than everyone trying to recreate that paper from the rough text description, which always leaves a lot of details out. So that was kind of the idea behind TensorFlow, and then we saw a lot of applied uses of AI that we thought having a framework like that would be really useful for people. Things we did wrong, I think, well, first, we didn't have kind of this eager execution mode that has been popular in frameworks like PyTorch and JAX and has been added to TensorFlow. So I think that kind of improved the abstraction further. And then the other thing we did wrong was in the open source release, we created a subdirectory called contrib. And we allowed lots and lots of different external people to contribute all kinds of different sort of helper libraries and things, ways of doing things. And I think that just confused the community a lot. Like we should have kept the core TensorFlow release without that directory, because what ended up happening was there were 10 ways of doing everything, depending on which subdirectory of the contrib thing or which particular sublibraries you use. And it would have been better to have those be libraries built on top of the core TensorFlow thing. So I think that caused a bit of confusion in the TensorFlow user community, which of these sub-contrib things should we use. So, always good to learn lessons from things. So we would not do that if we were doing it again today. But I think, it really did help lots of people around the world get introduced to machine learning, be able to start doing machine learning on important problems they cared about. And I think that's been good.
Yeah, thank you. Absolutely. Yeah. Thanks a lot for sharing this really valuable lessons and insights and so on. And I still remember before TensorFlow, a lot of people, including my students and other collaborators and so on, really, it took so much effort for people to just even implementing, the basic.
Yeah, and if you want to do anything at scale, you have to sort of build a distributed system underneath the covers.
Exactly.
And if you can sort of avoid having to do that and have a common abstraction, that's always a good thing.
Right. Yes, I also really loved the computational graph abstraction and so on. It was really elegant.
Yeah. As a compiler person, I like computational graphs.
Yes, absolutely. Yes. Yes. Thanks a lot for the great contribution to the field and so on. So now let's fast forward. So Gemini, of course, is Google's latest generation of frontier AI models, and you have really taken a significant, have made significant contribution in leading the effort as well. So now looking back on the development of Gemini, what surprised you the most, and what lessons from building Gemini do you think that you can share and can help shape the next generation of AI systems?
Sure. I think Gemini is really the culmination of a few earlier research projects, both within legacy DeepMind and Google Brain and other parts of Google Research. And at that time, we sort of realized that we were all converging to very similar kinds of directions, like trying to scale up the size of models we trained. We had some efforts, independent parallel efforts on how do you make language models also be multimodal so they can understand images and so on. And I wrote a one-page memo. I'm like, this is just silly. We should just all work together. Let's combine our people and ideas and compute resources and train one model that is multimodal from the start, that brings our best people together from across multiple research organizations within Google. And I think that was really good. My colleague Oriol Vinyals and I sort of founded the project and were the co-tech leads that started it. And we sort of brought people together. I had worked with Oriol previously because he was in Google Brain and then had to move to London for personal reasons, and so ended up moving to DeepMind. But we kept in touch, and so we sort of saw a way to bring ourselves back in closer collaboration. And I think that's been a really successful thing. I think the focus on making the model multimodal from the beginning has been really, really good. You want the model that you're going to use for everything to understand text and language and code and images and videos and audio and other modalities besides. So we put a little bit of, say, LiDAR data in the training data, so it at least knows that LiDAR data is a thing, because that's an important use case for further training of Gemini models. So that is important, and that's been, I think, a success of a decision we made at the very beginning to bring that through all the current Gemini models as well. I think we had a little bit, we wanted to make the model good at lots of things, and so I think maybe our focus on making it amazing at coding was lagging a little bit, and we realized that in our work to catch up on that, and I think we have good efforts underway. But I think by focusing on that, you end up with a system that is able to really do a good job of reasoning and doing other kinds of tasks where it needs to sort of work its way through breaking a complicated problem down into multiple sub-pieces and so on. And so that's a good, if you improve coding, you also tend to improve that capability in non-coding things. So.
Yes, yeah, that's great. Yeah, I mean, Gemini also started so many of the first advances and so on. Yeah, it was back then. Also, I was really impressed that Gemini was one of the earliest foundation models that, like you said, actually started with the multi-model from the beginning. Yeah. It's a big advance.
Yeah, and we've also worked on generative models, so having the ability to generate images and not just sort of use them as input, but also as output, and also videos, to generate audio, input and output. So.
Great. Yeah, thanks. So, so looking back, I almost call it the Midas touch. So essentially, this one thing that stands out about your career is that so many of these ideas, from MapReduce to MOE and so on, they actually took years before the broader community realized how important they would become. Like you had the Midas touch, and you had the special, really foresight to actually build and develop these ideas and systems and so on. So I think many people in the audience would love to learn, how do you do it? How do you distinguish between technologies that are genuinely foundational and those are simply fashionable? And what engineering principle that has remained surprisingly timeless throughout your career? And also, as AI shifts from models to increasingly autonomous agents, what new direction and new abstractions do you think we'll need over, the next few years and decades for future?
Yeah, I mean, it's a good question. I mean, I think I've been very lucky, maybe, as part of it. But I also think one of the things I try to do is keep track of a lot of different trends or research topics that the community is exploring. I often tell students it's better to skim 10 papers than to read one in detail, because you kind of then get 10 points in your cloud of what might be possible, or even skim 100 abstracts, because what you want to be able to do is connect important ideas that have not yet been connected. And sometimes when you think about a hard problem, if you have some of these things that are now kind of vaguely starting to be possible in mind, that can help you kind of shape a full solution to a problem, where instead of it seeming like 7 unsolvable problems, you can squint at it and say, okay, well, these 5 things, I know there's sort of vague work going on that seems important and might be able to address some of the things. And then there's 2 sort of additional things that I have no idea how to do, right? But if I work hard on them, I can imagine solving those. So that's kind of the perfect shape of a problem that you want to work on in a reasonably long-term manner, 5 years or something. Because I think the 5 areas that seem kind of not fully solved, but kind of are starting to take shape, and then the other 2 areas where you're going to have to sort of really think hard and figure out new techniques and so on, is to me, a really good level of risk to take on. You don't want to pick problems that are impossible and will take 20 years to solve and you have no idea how to do any of it. But you also don't want to pick a 2-year problem where it's very obvious what you need to do, because that's less about advancing the field in dramatic ways. It's more about practical engineering, and sometimes that's super important to do the things that are incremental improvements to what we're doing now. But you want to look for the things that are maybe very different ways of doing things that might be possible or might be possible soon. And I think one of the things that I also tend to use as an engineering toolkit is just being able to do back of the envelope calculations of okay, well, if I wanted to do that, how long would it take to process that much data? Or what if I needed to send all that data over this kind of network? Is that even feasible, or would that take 100 years? If it's 10 seconds, that's very different than 100 years, and being able to sort of mentally think through possible solutions or possible problems and understand the shape of solutions from those first principle kind of engineering, rules of thumb is a really, really helpful skill. And it's also something you can kind of do in your head and practice on your own. Like you're like, oh, I wonder how I would solve that. Okay, I would have this kind of thing. If I did it that way, it would be, this kind of approach. And if I did it this way, this kind of approach. And this one seems much better than that one because my rules of thumb say this would be 10x better. And I think that's just a good general engineering skill. It mostly comes from practice and repetition and seeing ways of other people solving such problems. So I don't know. It's not like I have any magic answer. And I've done a bunch of things that have not worked out well too. So that's also a good tip. Try lots of things that might not work. Some of them will.
No, thank you. Yes, this is right. These are great insights. Right. So to summarize, having a broad overview of the field and the trends where things are going, and also having a good balance, not too near term and not too long term where we don't even know where to start, and also being grounded in first principles and the underlying engineering principles. These are, right, yes, a great combination for people to potentially learn how to get this Midas touch. Yeah, thanks. So now let's look forward. So even just in the past couple years, Frontier AI has been making amazing advancements. So for example, even just, so last weekend, actually at Berkeley, we hosted the Agentic AI Summit with close to 5,000 in-person attendees and 100,000 joined online and so on. And we were really celebrating the huge advancements in agentic AI. But also at the same time, there was a lot of discussions actually with the underlying currents is that, well, we want the society to benefit from the great capabilities and power of agentic AI, but also at the same time, we are seeing increasing different types of risks. So for example, as you know, so my group, for example, we have been doing a lot of work in Frontier AI in cybersecurity. And my group, for example, we've developed like CyberGym, ExploitGym. These are leading benchmarks evaluation for evaluating Frontier AI's capabilities in cybersecurity that's being used by all Frontier AI labs, including their system cards, and it demonstrated the really fast increase in Frontier AI in capabilities in cybersecurity. And many people here may have heard about the recent incidents of OpenAI, Hugging Face, and others. So in this case, actually, OpenAI's agents were trying to solve actually tasks in ExploitGym in our benchmark. And the agent decided that there may be information from Hugging Face that could contain data that help the agent to solve the task. So the agent decided that they actually exploited several vulnerabilities and had a very sophisticated attack chain, and it lasted over 4.5 days. And the agent eventually, by breaking and exploiting vulnerabilities, breaking out the isolation environment, and also established some stepping stone through some third-party platform that eventually was able to actually compromise Hugging Face infrastructure and so on. And luckily in this case, the agent only tried to get data related to CyberGym and ExploitGym and didn't cause other harm. But however, in other incidents and also in the future, such behavior from agents can, of course, cause much greater harm and risks. So one question for you is, what's your thinking in this space? For example, also recently we have seen leaders issuing various open letters. Demis had a recent call for this new entity to help with AI governance, and Jensen had his call for open ecosystem, open way models, and Mark Zuckerberg called for building AI that benefits everyone and so on. And also recently, including me, over 1,000 leading AI researchers from Frontier AI Labs also signed this letter for pacing the frontier and so on. So I think this is on top of mind for many people. So what's your thoughts in this space?
Yeah, I mean, obviously, when people are building these models, they can be used for lots of different things, like lots of different kinds of technology. I think the vast majority of the uses of these models is incredibly positive for the world, like advancing, AI in healthcare and AI in education. Being able to make people able to solve problems they couldn't solve on their own will make people able to do more, and I think that's super exciting. Obviously, they can also be used to find security vulnerabilities, and that's a double-edged sword. You could use them to patch security vulnerabilities that exist, and there are lots of them in the world. And you could also, if you're a malicious user, you could use them to exploit them. I mean, I don't think that, yes, these models can now do things that sophisticated human cybersecurity attackers could also do, and maybe even beyond. But I also think they can find vulnerabilities that sophisticated human, cyber defense engineers might not be able to find. So there's always this balance of, people working to defend computer systems and people working to attack them. And I think they just now have much more sophisticated tools on both sides. I'm not a cybersecurity expert, but I think it is definitely a cause for concern. I think in a lot of cases, things you don't want models to do maybe have non-technical solutions, like you just make it highly illegal for people to break into computer systems. That's already kind of illegal. You could consider, what kinds of regulations would make sense in that space. And we will, as society, get through the kinds of things that we don't want these models to do and really promote the kinds of things that we want the models to do.
Yes, thank you. So great to hear your thoughts on this. Yes, so the important part is as Frontier AI makes these fast advancements, on one hand, right, we want the society to benefit from the good use cases. At the same time, it is important for society to develop both technical solutions and also these non-technical solutions to actually help mitigate the broad range of risks.
I actually worked on a paper a couple of years ago with a bunch of awesome colleagues, including John Hennessy and Dave Patterson and others, about 7 different areas where we thought AI was going to impact significantly, many of which are positive, like healthcare and education, some of which are kind of like geopolitical risk and computer security risk, which are less obviously purely positive, and then areas like job displacement, which can be a complex economic issue that many people at Stanford here are studying and looking at. So I think that paper is pretty interesting. It's my only paper with its own website, shapingai.com, because we had an ambitious co-author who set up a website.
Yeah, great, thank you. So looking forward, another topic that's generating increasing discussion is recursive self-improvement, where essentially AI systems, they can actually continue to improve itself, to learn to improve itself, and so on. And in particular, with this RSS recursive self-improvement, the speed of AI advancement could increase further and so on. This is also one of the key reasons that underlines the recent open letter that I mentioned, this pacing the frontier. I'm curious to hear your thoughts. What's your thoughts on recursive self-improvement? What's your timeline? How long do you think that will take? And also, as I know, this also relates to your now just started really exciting startup. So I'd love to hear your thoughts on that as well.
Sure. I mean, I think the idea of using machine learning to improve machine learning is not a new one. My colleague and actually co-founder Kwok Le and others sort of kicked off some of the early work in this space with neural architecture search, which is a way in which you can have a model generating model that generates machine learning model architectures and then evaluates how well those model architectures work on a variety of metrics, like can they learn quickly, what is the compute cost of training them, and so on. And then through an iterative reinforcement learning based process, the model generating model can get feedback on which kinds of decisions in the model architecture made sense and worked well, and which decisions seem to be bad ones. And over time, it learns to generate higher and higher quality model architectures that can learn more quickly and achieve higher quality.
Yes, I remember that's one of the earliest papers where the paper had a price tag of, I think, $1 million.
Yeah, I
several
think
million dollars.
that's list price. It was actually much cheaper than that internally.
Okay.
But and so it used actually very tiny models to evaluate how effective the architectures were. And as you learn which ones seem effective, then it would occasionally do experiments that were scaled up versions of those to evaluate, does that actually hold? And Kwok and others did some later work on the evolved transformer, which took kind of the basic ingredients of the transformer architecture and used an evolutionary algorithm to sort of find different ways of assembling it and mutating the components to then come up with a transformer that was like 30% more efficient than the plain vanilla transformer. So these ideas, I think, are really important. And recursive self-improvement is about how can you make the entire set of things that are necessary to go into a model get better in an automated way. And so often you have teams of people working on evaluating what kind of data is going to be most effective to improve the model's quality, or what kinds of evals are needed to help evaluate the model, and what kind of model architecture, as I mentioned. So I think you can actually have pretty effective automated loops of all of those things that are all working to improve that particular aspect and put those solutions together into something that can then improve the overall model and quality and mix of data and so on. And if you squint at a lot of modern problems in science and engineering, they actually all have this form of there's maybe a large problem that you need to break down into a bunch of subproblems. Then there's a subproblem, and you need to sort of figure out what a possible approach to solving that problem is. You need to implement and try that approach. You need to evaluate how well that approach worked, and then you need to iterate and get the feedback about how well that worked back to the process that's going to inform what is the next experiment you do. So science, this is the basic scientific method. This is the basic way in which you do engineering design, is you iterate on your design and you compare various attributes. So the idea behind our new company, Discovery Loop, which is a public benefit corporation, and our fairly ambitious mission is we want to automate machine learning, science, and engineering so that we can improve the rate of discoveries across many different fields. And obviously we're going to start with a narrower set of domains because we think that's important to have a little bit of focus initially, but we think there are a lot of reusable pieces of infrastructure and common techniques that are common across domains. And also by building models that are really good at understanding many, many different domains of science and engineering, you can get kind of PhD level expertise in a model across many different domains. And so no one human has PhDs in 20 different fields, but we think by having that ability, you'll be able to really figure out what are the important subproblems, orchestrate agents and multi-agent systems on solving some of those subproblems, recombining the results of the subproblems into solutions for the larger problem, and continuously iterating on these sorts of loops. And we think being able to run those iterative loops, each iteration, running those more quickly by building the right kinds of tools that can implement an experiment or evaluate an experiment quickly, so that you can, say, run an iteration of an experiment in a minute or an hour instead of a day or a week. And then being able to get feedback from running, thousands and thousands of experiments in parallel, and use that feedback to then decide what are the next set of experiments you want to run, will lead you to higher quality experiments that you run also. And so increasing both the speed at which you can run experiments and the quality of those experiments, we think is actually going to lead to something pretty amazing. And there's infrastructure you can build that manages like the whole set of experiments you might want to be running next, and tries to evaluate them in terms of like, well, what do I think the likely expected value of this experiment is, and what is the cost of the experiment in terms of compute resources or other things. We think that's a pretty exciting direction, and so that's what we're setting out to do. Me and my three co-founders, Sanjay Girmawat, Oriol Vinyals, and Kwak Lei. And it's super fun because we've worked together for anywhere between 14 and 30 years, and we've collaborated in pairwise versions on a number of different things, including a lot of the things you mentioned, MapReduce and Bigtable and Spanner and TensorFlow, and a lot of the things like model distillation and MOE architectures. And so we think it's just going to be a lot of fun to collaborate as a group of four and to build an awesome company that is working to advance scientific discovery. And as a public benefit corporation, we want to bring those scientific discoveries to as many people in the world as possible. So our goal will be to distribute those widely, and we might make decisions that are not in the company's financial interests, but are in the broader societal good of getting those discoveries out.
Yeah, so. Thank you so much. I mean, yes. That's a great vision.
And I've been working there for 12 and a half hours.
Thank you, Jeff.
I was unemployed at midnight for 1 second.
So thank you, Jeff. Thank you, Don. Now we open the floor for 2 questions. That one first. Please go ahead.
Thank you very much to our panelists for such an inspiring chat. My name is Joy Xie from Cheung Kong Business School in China. And I'm a shareholder of both Google and Meta, so I have 2 questions, if I may. One question for each. So the first question for Jeff, your resignation caused Google to lose 200 billion in market cap on the day. So it's clearly a big deal, in the eyes of the world. So my question to you is, what do you think you can achieve within a startup that you cannot achieve within Google? And also, one thing that puzzles me is with Google's compute and all the talent, what do you think that Google needs to do to catch up with, for Gemini to catch up with Fable? And my question to Don is, why Meta? Out of all the big tech companies, you must have offers from everybody. So why Meta? Thank you.
I'll go first. I think. I don't attribute things in the stock market to any particular events because it's always hard to.
It was you, Jeff.
I think first I have incredible fondness for my time at Google. I've been there 27 years. Amazing colleagues, so they're in good shape. They have a plan for making the Gemini models awesome. It's going to be great. And I'm excited to go off and do this. I think it's going to be really, really fun. Sometimes a focused small company with everyone focused on exactly that mission, and I think it's a great mission, is going to be amazing.
Okay, so I'll answer the question. Yes, so actually, a number of the leading AI companies, Frontier Labs, have reached out to me in the past, including Google. At the time,
it's because you do great work.
Thank you. But at the time, I wasn't quite ready to join big tech companies and so on. And also, I have been doing my own startup, as I mentioned. I actually have done 4 startups in the past. So the most recent one actually was acquired by Meta. At the time, deciding whether we wanted to join Meta, that was also actually a difficult decision. The startup was doing really well, and we have great customers in Fortune 500 companies and so on. But for Meta, I think also has a great platform. I think it's really, Meta Google, like really arguably the biggest distribution platform for Meta with billions of users and hundreds of millions of businesses on the platform. And with the technology that we have been building, really as the leading technologies for providing AI safety, AI security, and so on, I think can actually have a huge impact with such a big platform. So yes, with that, I'm very happy. And also, it's only been just a few weeks. Really excited to help. Thank you.
We have last question, this gentleman.
Hey, my name is Jonathan. I'm an engineer, so a big fan and user of your work. I promised I'd be asking this even if you didn't make a giant career switch 12 hours ago. Every first principles analysis of the AI industry would suggest that data is a large moat, so you need a large company to win. You need a lot for a distributed system. You need extreme capital expenditures, so large company would win. And you and your co-founders and individuals like Noam Shazir are evidence that excellent engineers can make outsized impact at a large company. And so I have a non-Google specific question, but I do want to ask for your inside baseball perspective. Why does it seem like a lot of AI talent retention and all of the frontier research, despite structural reasons for you assuming them to be happening at a large company, why is all of that seem to be still going towards startups? And this doesn't have to be a Google specific question, but why are small companies seeming to win over large companies when every conventional wisdom would suggest that large companies are absolutely going to dominate this industry?
Yeah, I mean, I think first there's the rise of cloud computing and, deployments of very large amounts of ML-oriented compute in various cloud platforms. And so that makes it possible for, a small set of people to, raise a fair bit of capital and be able to use those platforms without having to build them themselves, right? And so that, I think, enables people who have, a dream or a vision or a direction they think is really interesting to explore, to do that in a smaller setting than a company that has to sort of deploy all the infrastructure. And we can rely on amazing companies like Google, or other cloud providers to do a lot of the heavy lifting to build out the infrastructure that is needed in order to support, people's, idea of what a company should be. And we're super excited as a small company about working in a really focused way on science and engineering automation, because we think that's just a really ripe area for something. And we could have done that within Google probably, but I think the mission of 10 people in what we hope will be office space somewhere in Palo Alto, just focused exclusively on that, is just cuts through a lot of things that are slight distractions in a larger organization. But large organizations are awesome in many ways, and I have incredible friendships and have benefited from all the things that large companies provide in Google setting over many years. So it's a little nerve-wracking to go out without that kind of support. But at the same time, it's also exciting.
Thank you.
Okay, thank you. All right. I'm sorry we are out of time. I know there are a lot of questions, but I hope we can use AI to guess what Jeff and Dawn will be thinking. Thank you.
Thank you.